Welcome back to AI CodeCast. We're diving deep today into one of our recent challenges.
Yeah, this one's all about finding the shortest path, but there's a twist.
Oh, lay it on me.
Imagine like a city network, with roads connecting a bunch of cities.
Okay, got it. A network of cities.
But here's the thing, the roads keep changing. Like you're driving and suddenly, bam, new road.
Whoa, so like a dynamic map. That's pretty wild.
Exactly. So you start with, let's say, cities numbered from 0 to N1, all in a line.
Okay, like a straight highway going through a bunch of towns.
Perfect analogy. At first, there's just one road connecting each city to the next one.
Simple enough.
But then you get instructions to add new roads, one at a time, and they're one way.
Ooh, one way that adds a layer of complexity.
Right, and the challenge is, after each new road pops up, you got to figure out the shortest path from city 0 to the very last city, N1.
Okay, I see where this is going. It's like those navigation apps recalculating your route.
Precisely.
Yes.
Except we're not using an app, we're figuring out the algorithm to do it ourselves.
All right, challenge accepted. So how do we even begin to tackle this? Where do we start?
Well, the most basic approach is what we call brute force.
Brute force, as in just calculate the shortest path every single time a new road appears.
Yeah, essentially. You could use like breadth first search, BFS, or depth first search.
What is BFS? That's the one that explores the network layer by layer, like ripples spreading out.
Exactly. And the FS is like, go deep, explore one path as far as possible before backtracking.
But I'm guessing brute force isn't the most elegant solution here.
You got it. It works, but it's super inefficient, especially if our city network gets really massive.
I can see that. Recalculating the entire path every time would be a ton of wasted effort.
Exactly. It's just not scalable for a real-time situation. Imagine a network with thousands of cities and roads constantly updating.
Yeah, brute force would just crumble under that pressure.
So we need something smarter, something that can adapt to these changes without redoing everything.
All right, I'm intrigued. What are some of those smarter approaches?
Well, there's Dijkstra's algorithm, Bellman-Ford, and even a combination of topological sorting with dynamic programming.
Okay, those sound pretty advanced. But before we jump into those, are there any little things we should watch out for with this problem?
Absolutely. Remember those one-way roads? That's crucial. You can only travel in the direction specified, which can really mess with your shortest path calculations.
Ah, right. So you can't just backtrack if you hit a dead end. Got to plan carefully.
Exactly. It's one of those things that makes this problem more interesting than just finding the shortest path on a static map.
So any hints on how to approach this more efficiently, without giving away the whole game?
Well, think about it this way. When a new road is added, does the entire network change?
Not really. It's just one new connection, right?
Bingo. So maybe instead of redoing everything, we just need to figure out how that one change affects the shortest path.
It's like finding a detour instead of replanning your whole trip, right?
You got it. That's the kind of thinking we need to solve this efficiently.
This is getting me excited. Okay, I'm ready to dive into those algorithms you mentioned. Let's see how we can crack this code.
All right, let's start with Dijkstra's algorithm. It's a classic for finding shortest paths, but it's got a little twist that makes it perfect for this scenario. Dijkstra's, it's like BFS on steroids.
Okay, I like where this is going.
You see, BFS gets a little confused if there are different costs to travel between cities.
So like if some roads were longer or had tolls or something.
Exactly. But Dijkstra's, it eats that stuff up, no problem.
Because it's more versatile. But in our city network, all roads are essentially the same, right? Like one unit of distance.
You got it. So Dijkstra's, it could handle this, no sweat.
But it might be a bit overkill, right? Like using a tank to go grocery shopping.
Yeah, kind of. But here's the cool thing about Dijkstra's.
Yeah.
It can be tweaked to update shortest paths as new roads get added without starting from scratch every time.
Oh, that's pretty slick. How does that work?
So instead of recalculating everything, we just focus on the parts affected by the new road, like a little ripple effect.
So we're kind of just adjusting the existing shortest path based on this new road.
Exactly. We look at the shortest distances we already know and only update them if the new road offers a shorter path to a city.
That's way more efficient than starting over every time. So what about Bellman-Ford? How does that fit in?
Bellman-Ford, that's your go-to if you have negative costs.
Negative costs. What's that, like getting paid to drive on certain roads?
Yeah, something like that. But in our case, we're assuming all roads have a positive distance.
Right, because you can't have negative distance in the real world.
Exactly. So Bellman-Ford is super powerful, but not the best fit for this specific challenge.
Okay, so it's more specialized for those weird negative weight situations.
Precisely.
All right, so we've talked about Dijkstra's, touched on Bellman-Ford. What about that combo you mentioned earlier, topological sorting with dynamic programming? Those sound pretty intense.
They are. This combo really shines when you're dealing with a directed acyclic graph, or DAG for short.
DAG, right. Remind me what that is again?
It's basically a network where you can't end up driving in a circle, no matter what route you take.
Okay, so like a one-way road system designed to prevent traffic jams.
Exactly. And because our new roads are all one way, we're essentially building a DAG as we go.
Ah, I see the connection now.
And that's where topological sorting comes in. It lets us order the cities in a way that makes calculating shortest paths super efficient.
So it's like figuring out the most logical order to visit the cities, kind of like planning a road trip.
Perfect analogy.
Yeah.
And once we have that order, dynamic programming swoops in and does its magic.
Dynamic programming. That's another one that always sounds a bit intimidating.
It is a bit of a mouthful, but the idea is actually quite simple. It's all about breaking down the problem into smaller pieces and solving them one by one, reusing our work along the way.
So we're not calculating the entire shortest path each time, just figuring out how the new road affects things.
Exactly. It's like updating our knowledge strategically instead of starting from scratch every time.
This is blowing my mind. So any other algorithms we could use here? Or are we pretty much covered?
Well, you could potentially use Floyd-Warshall, but it's more for finding the shortest path between every single pair of cities.
Ah, so that would be a bit overkill, right? Like using a map of the entire world when you just need to get to the next town.
Exactly. It's all about choosing the right tool for the job. Dijkstra's, or the topological sort with dynamic programming approach, would likely be your best bets for this particular challenge.
Okay, I'm feeling pretty good about this now. But if someone were actually coding this up, are there any, I don't know, common mistakes they might make?
Oh, for sure. One common pitfall is not setting up your data structures correctly. Like with Dijkstra's, you got to initialize distances to infinity for all cities except the starting one.
Otherwise, the algorithm might think there's already a path there, even though we haven't built any roads yet.
Right. It's like assuming you can teleport before you've even built a road.
Got it. Any other tips?
Hmm?
Especially for those who might be new to graph algorithms?
Don't be afraid to draw it out. Seriously. Sketching the graph on paper can be a lifesaver, especially when things get tricky.
It's like visualizing the problem, making it more concrete.
Exactly. And remember, understanding the logic behind each algorithm is key. Once you get that, the code will come naturally.
Awesome advice. So we've covered a ton of ground here, from brute force to Dijkstra's to topological sorting and dynamic programming. What's the biggest takeaway for you from all of this?
You know, for me, it's really driven home the point that we got to be adaptable. The map's always changing, so our algorithms need to keep up.
Absolutely. It's not enough to just know one algorithm. We got to have the right tool for the job.
Exactly. Brute force might work for some things,
Wow.
but for dynamic problems like this, it just won't cut it.
We need something more sophisticated, something that can handle the twists and turns.
Right, like Dijkstra's, or that combo of topological sorting and dynamic programming. They're not just textbook examples, they have real-world applications.
Oh, absolutely. Think about GPS navigation, network routing, all that stuff relies on these concepts.
It's all about finding the most efficient path, even when the landscape is constantly shifting.
This deep dive has definitely given me a new appreciation for the power of graph algorithms.
Me too. And the best part is, we've only scratched the surface. There's so much more to explore.
Exactly. So to all our listeners out there, keep experimenting, keep learning, and keep pushing the boundaries of what's possible with code. Until next time on AI CodeCast.